Uh, all right. Just okay. All right. Let me just go to full screen and then we can start. All right. And put it here. Here is what it is. Okay. So. Welcome everyone to week 4 of this PMRF TA session for this NPTEL course, Approximate Methods in Quantum Chemistry. Brief intro of mine. I am a PhD student, Prime Minister Researcher of PMRF in the Solid State and Structure Chemistry Unit, SSU, at the Indian Institute of Science, ISC Bangalore. And I am an NPTEL-PMRF TA for this course, Approximate Methods in Quantum Chemistry. And there are total 8 2-hour interactive problem solving sessions which happens on every Saturday from 6 to 8 p.m. This session, week 4 session, 4th session, it is happening on Sunday because of some unavoidable reasons. Sorry, it has to be postponed. So it is happening today on Sunday on 26th February. All right. So in this week's session, we are going to discuss the content of the week 4, and week 4 content is on the perturbation theory and its application. So we are going to we will start with the unperturbed non-degenerate perturbation theory, the non-degenerate perturbation theory case, which was discussed. So we will start with a little bit of theory, and then we will also solve for the second order energy correction. The formula you must have seen in the lecture. So I will derive that formula once. So that will just cover our theory part, and we will discuss a little bit more about the wave functions and the energy, how they something unique about these wave functions, that wave function correction. Then we will discuss a problem for the practice. Then later we will discuss a small problem on the Hellman-Feynman theorem that you have learned. And later on we will also discuss some similar problems on degenerate, a similar problem on degenerate perturbation theory as well. And in the end, we will try to see the assignment 4 solutions, which has give you an idea of how to solve problems regarding this concept. Okay, so let's go to perturbation theory. All right, let me just check once. All right, sorry. All right, I'll just go full screen again. Okay. Yeah. So let's talk about perturbation theory. So this is just a quick revision from the lectures itself. These are equations exactly from the lectures. So what happens in perturbation theory is that we have a Hamiltonian given, and we can write that Hamiltonian as some h cap naught plus lambda times h cap prime. Here, let me just let's back. Okay. So we know the solution of h cap naught, which is our unperturbed state, and and h cap prime is our extra perturbation, some potential that we have provided, some extra perturbative potential that you have provided, and to solve, and this lambda gives we multiply it by lambda to give it the strength. So if we go to lambda tends to a 0, then we will go to our h cap naught, which is our unperturbed state. We directly go to that. Okay, so we know, so we need to find this psi n and E psi n, En and psi n values for our complete Hamiltonian, and we know this h cap naught, from this h cap naught we know psi n of 0 and this. So in perturbation theory, what we did is we write our psi n as the psi n 0 plus the first order correction times lambda plus lambda square times the second order correction, and so on. Similarly, for the energy En value as well, we write the 0th order correction without any perturbation plus lambda times the first order correction and the second order correction, and lambda square times the second order correction, and so on. Then we put them in this in our equation, which is h cap psi n equals to E n psi n. So you will just put this your Hamiltonian h cap naught plus lambda times h prime here, your psi n formula and all, and then we compare the lambda 0 terms in the equation, and from there we get these three equations, and as has been derived in the class, we can find this energy correction value. So this is our first order energy correction, and its derivation is also provided within the lecture. And similarly, we can find the our first order energy correction to the energy value, eigen energy value, and similarly we can find the first order energy correction to our wave function as well. Then similarly, the procedure that was used for this to find this method, we can also find the second order energy correction also. So first what we will do is we will do this first order energy correction, and let me just check. Okay, let's just go with black. All right. So let's just do this first order energy correction once. How to derive this term. So okay. So do that. We have to find En of 2. So we will use our lambda square term. So we have this h cap naught psi n of 2 plus h cap prime psi n of 1. It is similar to what we did in the class for this psi n of 1. How we solve for them. So we just solve it for this second order energy correction once. 0th order sine of the second order term. We want the second order correction, yeah. So we do this lambda square term. One minute. Sorry, just one. Yeah, 1 minute. Just stop share screen again. Okay, yeah. Let's just go back to this one. Okay, yeah. So we have to do this lambda square term. This equation. This is that I'm writing. H cap naught sine of second order plus h cap prime of sine of the first order. En of 0 sine of the second order plus En of the first order correction sine of the first order plus En of the second order correction sine of the 0th order. All right. So now to solve this, what do you do? We will multiply in the similar manner. We will multiply this by a psi. Okay, I have to check this once. We have corrected the lambdas from the lambda items now. Okay, yeah. Okay, sorry. We'll just do this. Okay. Now, what we will do is we will multiply it by, let's say, some psi m or psi n actually. Okay, psi n of the 0th order only. Okay, so we will multiply our term. Let me just check. Actually, just let me sorry about that. Let me just check once. I'm not gonna waste for n equals to m, right? For n equals to m case. Okay. So let me just write it in the in the wave function form. Actually, in the cat form. This is our lambda square terms, and what we do is we will write it in psi n of 0. So let me just write it as psi n of the 0th term, h cap naught, psi n of the second term. Sorry about it, actually the bracket notation was not there. So okay, yes, okay, we are back. Okay, plus psi n of the 0th term, h cap prime, psi n of the first order term, that will be psi n. So we are basically multiplying this equation by psi n of the 0th order term. This is our lambda square terms. Okay. So for lambda square term, which is h cap naught sin 2 plus h cap prime sin 1, en of 0 sin of 2 plus en of 1 sin of 1 plus en of 2 sin of 0. We multiply by sin of 0 here. Sin of 0 h cap prime sin of 1, that will be equals to sin of 0 en of 0 sin of the second order plus sin of the 0th order, en of first order, sin of the first order plus sin of the 0th order, en of the second order, sin of the 0th order. If you remember, this is the same thing that was done to find the en of 1. So we put n equals to m, then we get this en of 1 formula, and similarly for the lambda to the power 1 term equation, and now we are doing it for the lambda to the power 2 term equation. So the procedure is just the same. Okay, now here you can see in this first term, it is sin n to the power 0, so h cap naught will apply on here, and en of 0 will come out, and what we have is psi n of 0 here, and psi n of 2, plus this term will remain the same, h cap prime sin of the first order. This will be equals to, again I can take this en of 0 out, en of the 0th order, sin of the 0th order, sin of the second order, plus again en of the first order we can take out, sin of the 0th order, sin of the first order, plus en of the second order take out, sin of the 0th order, sin of the 0th order. All right. Now here you can see I can cancel out these two terms, en to the power 0, sin to the power and these terms. So these two terms got cancelled out from both sides. All right. Okay, and let's say, and these are the remaining terms. Alright, so I can write it here as, continuing with this. Okay, now what we can write here is that we can write psi n of 0 h cap prime minus en of the order 1 psi n of order 1 first order correction, that will be equals to en of the second order correction, sin of the 0th order correction, they are and that will be equals to 1. Okay, this is also one thing. Yeah, and this will be I can just use this one. So this will be equals to 1. This thing will be equals to 1 because normalized wave we will take the normalized wave functions. So this will be 1. So en of 2 is coming as this. Okay, so what we are getting is our second order energy correction is just coming as psi n of the 0th order h cap prime, this is our perturbation, on psi n of the first order correction. Okay, so sorry, and we have en of the first order correction, psi n of the 0th order correction, psi n of the first order correction. Okay, now here using the formula, now we know that for sine of the first order correction, you know that in this there is no psi n of the zeroth order. So we know that psi n of the first order correction will be perpendicular to sine of the zeroth order correction. This we can see from this psi n of this formula, because m is not equals to n. So this term is also actually equals to 0. So yes, this will be 0. That first one, this will be 0. So we simply get En of the second order correction will simply come as sine of the zeroth order h cap prime sine of the first order. Now using the formula that we have derived for sine of the first order correction, this formula, we can write summation of m not equals to n, this will be sin of the zeroth order h cap prime, and you have to write sine to the first order will be psi m of the zeroth order. We will have psi m of the zeroth order times psi m of the zeroth order h cap prime psi n of the zeroth order divided by E n of the zeroth order minus E m of the zeroth order. All right. So, and these are just the complex conjugate to each other. From here, we get E n of the second order comes as summation of m not equals to n, and this you can take the minus sign here, and you can write it as psi n of the zeroth order. Okay, let me just see what the formula is. Okay, psi m, in the psi m form we can write. Psi m we can write first. Psi m of the zeroth order. I'll not bring the minus sign because we don't have minus. H cap prime psi n of the zeroth order whole square, because that is just the complex conjugate, divided by E n of the zeroth order minus E m of the zeroth order. So this is our formula for the second order energy correction, and you can check like, okay, we got the same formula. Sometimes psi m of the zeroth order h cap prime sine of the zeroth order whole square divided by E n of the zeroth order minus E m of the zeroth order. So it is the same process as for the first order energy correction. All you have to do is you have to take the lambda equation of the lambda square terms. All right. So this is just a quick proof of that. Then other than that, we can discuss one more thing about this wave functions. Some more relations that we can derive. So let's just see some more relations. Okay. All right. So let's say we have okay. Now we have our wave function, but we have written our psi. I will write it in cat form now. Okay, so our psi n wave function we have written at psi n of the zeroth order. All right, plus we will write it as lambda times psi n of the first order correction and lambda square times psi n of the second order correction, and so on. All right. Now let's say you want to normalize your sine wave function. Okay, we want sine to be normalized, All right. So what we need is psi n has to be equals to 1. This is our wave function after the perturbation. So our total wave function, where we are getting by adding this from the zeroth order correction, we are adding this first order second order correction. Now if you want to normalize it, then we will have this, and if I write this equation there, what we will have is we will get terms like, sorry, we can have psi n0, psi n0. Okay, then okay, so we will just do sine, and then we are combining all the lambda to the power 0 term, lambda to the power 1 term. So for lambda to the power 0 we will get this. For lambda to the power 1 term we can get sin of 0, sin of 1. Alright, and what we can get is sin of 1, and right, we can get sin of 1 and sin of 0. Then for the lambda square terms we can get sin of 0, sin of 2 plus sin of 1, sin of 1 plus sin of 2, sin of 0 term. All right. Okay, so we will get something like this. It is the 0th order term, then 0th order, and then the first order term. All these terms. Okay, and we know that this sine of 0 that is also 1. All right, we know that these are normalized. 0th order, so it will be 1. So so what we are getting is that this is becoming 0. The 1 equals to 1, and all these, so basically all the lambda terms that they have to be, all the coefficients of this lambda, lambda square, and so on. Okay, and so on, whatever our other terms would be, all these coefficient has to be 0 if you want our sine function to be normalized. Okay, now from this relation what we are getting. Okay, now from the lambda coefficient, what we are getting is that sin of the 0th order, sin of the first order, plus sin of the first order, sin of the 0th order, they has to be equals to 0, and they are just you can see compressed, they are just compressed conjugate of each other. So then what we are getting is sin of the 0th order, sin of the first order should be equals to sin of the first order, sin of the 0th order has to be equals to 0. So this is one relation that we can find from here. Alright, so this is an relation. So what we have found is that the first order energy correction wave function will be orthonormal to the 0th order energy correction, and that we got from here as well. Okay, when we derive this sine function, we can see that okay, m is not equals to n. So from here also we can say that it is perpendicular, and here we have explicitly proved that this wave function of the 0th order will always be perpendicular to the first order energy correction wave function. So for any value of n, it will be true. Right. So this is a proof area. So we have proved that. We have proved that first order correction wave function is perpendicular to the unperturbed state. All right. So this thing we have proved. These are some some additional proof that we can do. Here also they are the complex conjugate, and you can take some. We can make, since these are just complex number. You can take. Sorry. 1 minute. 1 minute. So you can make them real as well. Just put this thing here. Okay, I can write one more thing that I can write about this is that this face on psi n of 1 can be chosen to make psi n of 1 psi n of 0 real. Okay, so we have put these values as 0 because you can see they are just actually the complex conjugate each other, or you can actually choose some phase to make this real as well if you just want to deal with the real stuff. But basically they are complex conjugate, and you can easily see that for this equation to be true, this condition has to be there. The first order correction has to be perpendicular to the unperturbed state. Okay, now let's see what we can get from the lambda square coefficient. All right. Okay, lambda 1 comes, we get this. So from lambda square term, what we need is we need sin n 0, sin of 2. Actually, yeah, we will use this thing. Actually, face on sin 1 can be chosen to make. Okay, so we can choose this face on this sine wave functions, so that our this sin 1 and the this sin 1 sin 0 coefficients, they become real. So we can choose this kind of wave function, and we will use this property here as well. So sin 0 sin 2 from lambda square term plus sin 1 sin of the first order, sin of the first order, plus sin of the second order, and sin of the 0th order. This also has to be 0. Now we can here also sin n of 0 and sin of 2. Now these are complex conjugate, but we can choose them to be real, because it is by choosing arbitrary phase of psi n of the second order. So we can change this sign of the second order wave function, and we can make this complex conjugate as real. So if you do that, then what we get is sine of the 0th order, sine of the second order will be equals to sine of the second order and sine of the 0th order. The second order will be equals to sine of the second order, sine of the 0th order will be equals to minus 1 by 2 of the sine of the first order and sine of the first order. So this is another relation that we can find. So basically using this normalization technique, we can find this different kind of relations between these wave functions. Alright, so this we can find, and mainly we have important thing is we have proved this thing using this normalization of this wave function. We have proved this thing that the first order correction will be perpendicular, and we know that when we derive the formula also, from there also we can see that thing. All right. Now let us do some a problem. Okay. A problem. Okay, let us do a problem to get more practice on this perturbation theory. So let's say you have a, let's say if your perturbation h cap prime is given as a matrix 0 v0, or let me just write what I mean by 0 v0. So h cap prime matrix, I will write this in a matrix form. So that will be psi n of 0 h cap prime. Let's say we have two states, psi 1 of the 0th order, psi 1 of the 0th order, right? Okay. Okay. Let me just let the perturbation h cap is given. Okay. Let the perturbation. Is given by the h cap prime. Alright, so I will write this h cap prime as a matrix. When I'm writing matrix, I mean for a two energy eigenstates, two eigenstate system. Psi 1 and so we have two. So, okay, so let's say we have a system. Okay, we have a system of two eigenstate system. Let us consider two eigenstate system, psi 1 and psi 2, and we are providing a perturbation h cap prime, which I will write it as psi 1 h cap prime psi 1 h cap prime psi 2 h cap prime. Okay, let me just write in the 0th order actually, because we are doing perturbation theory. So psi 1 of the 0th order, and we have a psi 2 of the 0th order. Alright, psi 1 of the 0th order h cap prime, psi 1 of the 0th order, and you will have psi 1 of the 0th order h cap prime, psi 2 of the 0th order, you have psi 2 of the 0th order h cap prime, psi 1 of the 0th order, and psi 2 of the 0th order h cap prime, psi 2 of the 0th order. That is given by this matrix, is given by our non-diagonal matrix 0 0 VV. Okay. Now the problem is find the first order and second order energy correction. Okay, so we will try to find the first order and second order energy correction if we have a system with two eigenstate, and the perturbation is given by this kind of a matrix. Okay, so this is our problem. Okay, now to solve, now we know that for the first order corrections, now we know that for the first order correction, order energy correction, that is simply given to us. Let's say it is given by matrix V. Okay, I'm writing this matrix as a V matrix because the notation was H prime, so I went around with this. So let's say our matrix is the sum, or just go with H cap prime only, as H prime only. Let's write it as H prime. Since this is a matrix, it's better to write it in this without H cap. Okay, so I will write it as H prime. Just write it without hat actually. Okay, H prime. Alright, so we have an H prime matrix. You can write this as matrix in form this H11, H12, H21 and H22 as well. Alright. Now first order energy correction. We know the formula. You can see the formula En of the zeroth term. En of the first order correction. And this psi1, psi2, let us consider they are psi1, psi2, they are orthonormal. They are normalized wave function. Normalized wave functions. All right. So from the first order energy correction formula, we know that it will be the sine 0 H cap prime sine 0. So first order energy correction, En of the first order correction will be just equals to psi 1 of the 0th order H cap prime psi 1 of the 0th order, which what is this? This is actually H11, our H11 matrix element, and that is given as 0 in this case actually. So our energy correction E1 is coming 0. Similarly, for the correction to this second state, H cap prime psi 2 of the 0th order again. So this is coming as our H22. You can see this is H22. So I have taken a very simple matrix. Mainly we just have to determine this matrix element, and here the matrix element is given as 0. So what we are seeing is that there is no first order energy correction because of this kind of perturbation. So if you have some this kind of a constant perturbation where your diagonal elements are coming 0, then you have no first order energy correction. The first order energy correction in this case are coming 0. So what does this now? And also actually first order energy correction, and you can also find the wave function. Also first order correction too. Also find first order correction too. Correction to the wave function. All right. Let us try. Okay. Let us find the first order correction to the wave function. Correction. And to find that, so sine of the first order. Okay, we have this form again. We just have to use the formulas. Sine of the first order correction we are given. Sine of the first order correction. Write the formula again. So we have summation hour. Okay, let us write the first order correction. We know the formula. Let me just. I will not write the formula again. Or let me just write the general formula once. It is summation of m not equals to n psi m of the 0th order H cap prime psi n of the 0th order divided by E n of the 0th order minus E m of the 0th order times psi m of the 0th order. Okay, So using this general formula, psi1 of the first order, that will be just equals to, or I'm going to be psi2 of the zeroth order h cap prime psi whatever n is 1 of the zeroth order divided by e1 of the zeroth order minus e2 of the zeroth order. Okay, so and in this case what we have is this is equals to v, this simply equals to v. So what we have is this is given by, let me also mark our answers. So this is our first order energy correction. So first order energy correction is coming because of that perturbation 0, and here we are getting v divided by, and this will be e1 of 0 minus e2 of 0. So and we know that okay, the first order, this energy will be equals to the okay, so I will write this as delta E. Okay, I will write it as delta E with a minus sign. So because so we will draw a diagram where delta E will be fixed. So this delta E is equals to E2 of 0 minus E1 of 0, because we know that we are taking the first order and the second two energy state we are taking. So we are taking like psi1 is lower energy. I should have mentioned it, but just mention it here. This is lower energy state, and this is the higher energy state. Although when we state 1, state 2, they are explained already. So this is equals to this. So this will come as this, and psi of the second psi 2 of the first order similarly will be given by psi 1 of the zeroth order h cap prime psi 2 of the zeroth order using the formula divided by e2 of the zeroth order minus e1 of the zeroth order, which will be equals to v divided by delta epsilon. Alright, so this is our first order energy corrections to the wave function. Now what we can see here is that okay, so what we are seeing is we have two states. We have a psi 1 state, lower energy state, and we had a psi 2 state. Let's say the energy difference between them was delta epsilon. So after applying this kind of perturbation, if we just go up to first order correction, so what we are seeing is that the energy values are not changing. So if we apply let's say I'm applying a V on, I apply V on, and I'm taking only up to the V0 and only first order correction, only up to first order. So what we will see is the these energy values, they will just be there. The energy level will not change. Okay, the difference will also remain delta E. Only the wave function will now change. So our psi 2, okay, these were our zeroth order corrections. Okay, this was our zeroth order. So these were our zeroth order wave functions of the zeroth order. This is the low energy state and the high energy state. Delta is just the difference. So so in this case, delta E remains the same if we go only up to first order correction. Only up to first order correction, then this remains the same. But our psi 2 will be this psi 2 of the zeroth order, and the correction that we are saying is will be plus V by delta epsilon. So there will be an plus sign in here, while what we get here will be psi 1 of the 0th order, we will get a minus sign within the wave function. So our wave function is changing just by the first order up to first order correction, but our energy eigenvalues are not changing. All right, now let's just go to our second order energy correction. Second order energy correction. Okay, now for the same potential, we need to find what will happen for the second order correction. If you go up to second order corrections, yeah, okay. So if we do up to second order corrections, again the second order correction formula that we have, let me just write it in the formula again, m naught equals to n mod of psi m of the 0th order h cap prime psi n of the 0th order whole square E n of the 0th order minus E m of the 0th order. Alright, now using this, for the first order correction, what we will have is psi 1 of the 0th order h cap prime, okay, it will be psi 1 of the 0th order h cap prime psi 2 of the 0th order whole square divided by E n is equals to 1 and m will be 2, because n is the state in which, so whenever you have to solve this type of questions, n is the state in which the correction is. So we are finding the correction in energy level 1, and m are all the other states. So whenever you have to put the values, just put it properly. So m is with, sorry, here I have done actually wrong. So this will be actually, so m will be our 2 and n is 1. Psi 2 0, h cap prime psi 1 0, E 1 0 minus n is equals to 1 and m is equals to 2. Now psi 2 h cap prime, this is h21 and h21 is given from our matrix, that is given as 1, v, that is given as v. So what we will get is v square divided by, again I will get a minus sign and delta E, because it will be minus v square 1 delta E. While our second order correction for the second state, let me see if I did here also I did this correctly, no? 2 and n equals to 1, n equals to 1, m equals to 2. Here n equals to 2, m equals to 1, and m equals to 1, and n equals to 2. Yeah. So okay, so we just have to use the formula and just remember that n is the one we are changing. So now again here m will be equals to 1 and n will be equals to 2. So this h cap prime and n will be equals to 2 now, psi 2 of 0 whole square divided by n will be equals to 2 E2 of the 0th order minus m will be equals to 1, because m is the other one and n is the one that we have to change to E2 and E2 here. Alright, again this psi 1 0 h cap prime h12, you can check h12 is v, so that will be v square upon delta epsilon. So we have some what we can see that up to, if we go up to second order energy correction, then we will get some change in our, there are non-zero values, and how you can see it as okay, actually I have to use this one. All right, so so what we are saying is, so now we have this energy state. We had this psi n of psi 1 of the 0th order, and this is psi 2 of the zeroth order. All right. Okay. Now the energy value didn't, and this was delta E. This is delta E. And if we apply a V on, okay, so up to the first order correction, we know that there was no change. We have applied V, which is 0 0 VV. All right. Now up to the so they will remain on the same energy level here. This is only up to first order correction. But now we will go to the second order correction. So if you go to the second order correction, so what will happen now is these energy values, as you can see, the E2 value, it will increase. So E2 value will increase while the E1 value is decreasing. So this is what we are getting if we go to the up to the second order correction. So these are our new energy levels, and this energy difference has now changed from delta epsilon plus 2V square by delta epsilon. This is considering second order energy correction. So if you consider second order energy correction, then we are seeing that the delta is changing, and what we are seeing is that as a result of second order energy correction, the energy levels repel. So the energy levels in this kind of potential, they start to repel. So what we are seeing is that so just by applying this kind of potentials, if you apply potential, so maybe up to first order you might not see any major difference, but now you are seeing that they might even start, they behave like they are repairing. So like because of this perturbation, these levels are now repairing each other, energy levels, and thus our energy gap is increasing. Okay, so this is an example of perturbation theory, how to use basically these equations and formulas. All right, and now let us move on to next problem on perturbation theory. All right. Okay, so sorry about that. Let me just. All right. Okay. So let's just solve one more problem in perturbation theory. Okay. So our problem is this one. Suppose that a ground state harmonic oscillator experiences a constant perturbation. Okay, so let's say we have a ground state harmonic oscillator that experiences a constant perturbation A during expansion. That is, for x greater than or equals to 0 only, it experiences a constant perturbation. Determine the second order energy correction to V equals to 1 state. Okay, so now so our psi1 of x function, okay, psi1 of x function, let me just first write the psi1 of x. So what it is saying that suppose that, so we have a ground state harmonic oscillator, 1 minute, so we have a ground state harmonic oscillator Okay, so this is so we are considering in 1D only. So this question is being done in 1D only. We have a ground state harmonic oscillator like this at x, and suppose, and what we are doing is experience a constant perturbation A during. So we are providing a constant perturbation A for x greater than 0 only. So this is our constant perturbation. Let's say this is V, and I have provided this V of x, function of x, and we are providing a constant perturbation V here for x greater than 0. This is our origin 0. So after that we are providing a perturbation here which is of magnitude A. This is a constant. So there is a constant potential, external potential that we have given out of it. So this is our problem, and we have to determine the second order energy correction due to this on V equals to 1 state. All right. So so our h cap naught we already know what our h cap naught is. Okay. So let's just write our h cap naught. H cap naught is equals to minus h pi square by 2m del square by del x square, or you can write px. You can write it px square by 2m and half m omega square x square. Right. This is our h cap, and our h cap prime is basically 0 for x less than 0 and is equals to just a constant A for x greater than equals to 0. So here this is a constant potential, so you know we can find the now in the question we have the second order energy correction due to the V equals to 1 state. So so we just and so psi 1 of x. What is our 0th order state? So for V equals to 1 actually we have taken. So I'll just take this. So I will write this as psi 1 of the 0th order. So we will take two energy values. Okay, let's just take okay 2 energy values. So we know that psi 0 of x, psi 0 of the 0th order of x, that is given by alpha upon pi to the power 1 by 2 whole to the power 1 by 2 e to the power minus alpha square by alpha square x square by 2. All right, and psi 1 of the 0th order, that is given by 2 alpha cube upon pi to the power 1 by 2 whole to the power 1 by 2 x times e to the power minus alpha square x square by 2. Okay, this we know from our simple harmonic oscillator. Right. Then what we have in here is now here h1 now we need this second order energy correction. Again we will write what was our general formula for the second order energy correction. We don't have to find the first order, we have to find here directly the second order energy correction. So this is just a little calculation problem, but yeah, so you can see how psi m of the 0th order h cap prime, okay, h cap prime psi n of the 0th order whole square divided by E n of the 0th order minus E n of the 0th order. All right. Now we need to find this correction for the V equals to 1 state, which is this state. We need to find energy correction for this one. So E1 of the second order energy correction will be given by, so again you have n equals to 1, and let's say we are just considering from the ground state contribution only, due to the second order energy correction due to the V equals to Okay, so we have to consider only due to v equals to 1 state. Okay, sorry. So we have to find the energy correction. We are finding energy correction to our ground state. Okay, we are finding energy correction to our ground state, but only up to the one term, only because of this psi1 state only. That we have to do actually. Yeah, so we have to find the first order correction to our second order correction to our ground state, but only because of one excited state, which is psi1 of x. So here we will have m equals to 1, h cap prime psi 0th of the 0th order whole square divided by e 0th of our ground state minus e1 of the 0th order. All right. So this is what we have. This is what we have to solve. All right. So now we know that now the energy value for this. Now we know that for the harmonic oscillator, this En is given by n plus half h cos omega. So from here we know that E 0th of the 0th order, that is just equals to h cross by 2, all right, and E1 of the 0th order, that is equals to 3 by 2 h cos omega. So from here, first just find the denominator, which is easier thing. E1 of the 0th order, that will come as h cos omega by 2 minus 3 by 2 h cos omega by 2, which you know should have come. So it will come as minus h cross omega. Okay, so we have found the denominator, which was easy. Now we just need to find this matrix element, which is psi1 0 h cap prime psi 0 0 whole square, and then we are done. So let's find this matrix element. We have psi1 of 0 h cap prime psi 0 of 0. All right, we need to find this matrix element. So that will be just equals to, you have to do your dx integration from 0. Now let me just do it first from minus infinity to infinity. All right, now from minus infinity to infinity we will do, you have to just do psi 0 of x h cap prime psi 0 of the 0th order of x. Okay, now we know that our h cap prime is actually 0 up to x less than 0, and for x greater than 0 it is just a constant a. So our integral, so our matrix element now will be just given by integration from 0 to infinity dx. Now we will have psi1 of, it will be star, but as we know these are real function, this is real, so I can just write it as this because these are real function, times a constant a, we just have a constant, times psi 0 of the 0 order of x. Okay, so this is the term that we have. All right. Okay. Okay, so psi 1 we have this h01 first. Okay, let's check once. It's a constant, no? Okay, so so we have to find this integral. This integral will be equals to dx times whatever a we have. Now psi 1 of 0 of x can write that 2 alpha cube upon pi to the power 1 by 2 pi to the power 1 by 2. Okay, yeah. Yeah. So, here, remember that this is a constant. So, what you might also get confused for a second. I also got confused. Yeah. So, one might think that okay, these are actually eigenvectors. So, doesn't this integral should be 0? Shouldn't this value should be 0? So that is just side element. The integration is from note integration is from 0 to infinity. Note integration is from 0 to infinity. From 0 to infinity. So this integral is not 0. Integral is not 0. Yeah, so this is if someone but that just comes because whenever we see this kind of terms, we say that psi1 0 of x is orthonormal to psi 0 of x. But that will happen if you have an integration from minus infinity to infinity. Now we have integration from 0 to infinity, so it will not be orthonormal. So for a second I also got confused. So just in case if you also get confused, you think that why we are integrating, why it is not directly 0, because that orthonormality you have to integrate from minus infinity to infinity, then that will be complete. Then the complete integration will be 0. Because of orthonormality. Okay, now we just have to do the integration actually here. So we have psi 1 of 0 of x. We can't just write it as psi 1 of 0 to alpha to the power. So you just have to put this equations. Let me just not do this integral right now. Don't have enough time. Okay. Let me just. Okay. Psi 1 of 0th order x, that is equals to this term. Just capture it. Okay, I can't copy this somehow. So basically you have to put this psi 1 of 0 of x that is given, and you have to put, let me just solve this once, 2 alpha, sorry I have to check actually this equation, 2 alpha cube upon pi to the power 1 by 2 to the power (1 by 2) x e to the power minus this will be alpha. Okay, I made okay, these are alpha. I've written alpha, no? Okay, and alpha square x square by 2 times a constant a times alpha upon pi to the power 1 by 2 whole to the power 1 by 2 e to the minus alpha square x square by 2. Okay, so we have to do this integration, and the integrations come as a times, I'm just writing the answer directly here, 1 by 2 alpha square upon pi to the power 1 by 2 1 by 2 alpha square, which will come as a upon 2 to the power 1 by 2 and pi to the power 1 by 2. Yeah, so so this is a simple integration, and you can do it by you can check the integration table as well. And this kind of integrals has been done earlier in the course as well. So just by doing this integration, we get this result. Okay, so we have our matrix element also now. So our correction first order correction to this energy only because of the one excited state. So we need the square, we need the square of this term. Let me just write again. This was psi 1 of 0, okay, psi 1 of 0 h cap prime psi 0 of the 0th order whole square up to this second order correction. Sorry, this was up to second order correction we have to find. Psi 1 of the 0th order h cap prime psi 0 divided by so we will use this thing, we are using this thing that we have calculated. This is our formula that we are using, E0 of 0 minus E1 of 0. Of the 0th order, okay, psi 1 of the 0th order h cap prime psi 0 of the 0th order whole square E0 of 0 term and E1 of the 0th order. Alright, so denominator we got is minus h cross omega. Okay, we got minus h cross omega, and the last term that we have obtained, which was this psi 1 of 0 h cap prime psi 0 of 0. And also, since these functions are real, this will also be equals to its complex conjugate. This is real. Okay, let me just mention that this is real. So you can just take the square on mod square will just square of this. This is real also. So you just have to take the square here and just putting square value, which will be a upon 2 to the power 1 by 2 pi to the power 1 by 2 whole square. Yeah. So that gives us a square upon 2 pi times minus 1 upon h cross omega, or we get a square upon minus a square upon h cross omega. So this is our final answer. Our 0th order correction just because of one state, excited states, come as this. Alright. So this is our final answer, and so here 8 times, yeah, alright, correct, come 8. So you just have to so this is how we generally solve any kind of problem in perturbation theory. You just have to use these equations, and just remember that we have to put the n and m. N is the one that we are changing, and m are the excited states that we are using to change our nth state, to find a change in our nth state because of the perturbation. Okay, nth is the one that we are changing, and m are the other excited states, other states basically. Because of combination of them, we are getting our change in our nth state. All right. So that is just a simple question. Okay, now let's talk about Hellman-Feynman theorem. So I discussed in, just a quick recap. So what Hellman-Feynman theorem does is if we have a Hamiltonian and our Hamiltonian depend on some parameter p, then what we can find is that we can find our energy value as psi h cap psi. Then what will happen, since our Hamiltonian also depends on a parameter p, our energy values, they will also depend on a parameter p. And if we take the differentiation of that dE with respect to dP, then as shown in the lecture, what you get that will be just equals to expectation value of that dH cap by dP. So this is a very useful theorem as you saw in the lecture as well, and the application for this in the perturbation theory of electric field. So here also this is just a small problem to understand how to use this Hellman-Feynman theorem. So let's say the problem is if the Hamiltonian of the system varies with a parameter p as just hp x square, give an expression for the dependence of the energy of the system on p. Okay. So since we know that our Hamiltonian h cap, which is given by p x square, now it depends on p. So we know that our energy will also depend on p. And using Hellman-Feynman theorem, dE by dP, how energy will depend on this, which is be given by expectation value of d of h cap by dP. Here h cap is given by d of px square by dP, that we just expectation value of x square. So this is the expression that was asked to us. So by this we can, so this is just a very simple question to understand how to use this Hellman-Feynman theorem. We just have to use this formula. Alright. So let's move on to the next problem, which is the perturbation theory for degenerate case. Alright. So the perturbation theory for degenerate case, this has been discussed in a class where we have taken like degenerate states. So what we can do is, let's just consider a 2-4 degeneracy, and we will derive the similar kind of equation just for the 2-4 degeneracy. Okay. Okay, so just to do a question. So let's just consider to understand how this degeneracy. So in a proper way to understand, like instead of considering like D4 degeneracy, let's just consider 2-4 degeneracy. Let's see. Okay. So so we will derive the similar equation, but for the D4 degeneracy case, and we will solve all the problem. Let me just check, we did it for the D4 degeneracy in the class. Okay, and we will derive it for the screen. Okay. So if we consider 2-4 degeneracy, let's say our h cap naught, that is given by so I'm going to use some different notations, maybe let us go with that notation only. Okay, let's say we have, I'm doing this 3 or 4. Okay, 2-4 degeneracy. So what I'm saying is, let's say we have a system. Let's say we have an energy state, which, let's say we have an energy state like this. So we have a 2-4 degeneracy. So I will call this state. I'm taking some notation as this. Okay. So what we have basically seen is that what happens when we apply this for the degenerate states. Whenever we apply, we will get a determinant form, and we will get what we will get is our new wave function will be a linear combination of these degenerate states. Okay, so in the 2-4 state, you can consider that that is kind of rotating. We are kind of rotating them as well. But let us go with this 2-4 degeneracy example, and then to understand, to see how you get this term. Like we can get this equation for the D4 degeneracy, but we can solve it more explicitly for the 2-4. Let's say this is our psi function. Okay, so let's say we have a 2-4 degeneracy. So let's say I have some psi function of second order, second energy state of the zeroth order, or psi n. Okay, let's just go with psi n of 0, psi n state of the zeroth order, and it just has a 2-4 degeneracy. So for 2-4 degeneracy, I will say it has some state A, which gives you some, let's just go En of the zeroth order, again sin of the zeroth order with state A. Similarly, we have h cap naught sin of the zeroth order B is equals to En of the zeroth order sin of 0. So I'm going to solve this problem without using the that determinant. So we did it for the D4 degenerate case, but instead of that, what I'm doing is I'm not gonna do. I'm just going to do this for this D4 degeneracy. And what I know is that what will happen is, if we have sin of the zeroth order, this A state, and sin of the zeroth order 2-4 degeneracy, and what happens if I do a perturbation on and off. Okay, so this is my perturbation. So in the degenerate case, what was happening is that as it was told, basically what will happen is that there was a reason that when we switch off the perturbation, then we should be able to go back to a wave function, and that's why we say that our this wave function is going to be a combination of this degenerate states, as it was explained. So similarly, by this, what we can say that, let's say our state goes to some state L. This is of the zeroth order A, and this will go to some L0B. Okay, and this will be restored. Okay, so this will be restored, as has been said in the class, because so these will be some combination of, we know, of sin 0 of A and sin 0 of B, but we are not writing them explicitly. We are saying that okay, they will go to some L0 of A, L0 of B. Now for the unperturbed, now under perturbation, and they will be restored. Okay, what I am saying is that because of this, if I apply the perturbation and if I then switch off the perturbation, then also the zeroth order state will now become some combination of the of our degenerate states. So that is also what was told in the class as well. For the if you have D4 degeneracy, then we take a phi n of the zeroth order. We took a linear combination, and this is in the same way we are just doing for the just taking only 2 degenerate states. But that is the thing, when you apply this potential and then you switch off the potential, then afterwards it will be restored. It will be you will have states which will be some rotated state. If you just have 2, then it will be rotated. Okay, now under perturbation, what will happen is, I can write this L of A. Now so what I'm doing is, instead so I'm also doing the same. So for these 2 orders also, we are saying is that let's say they will convert into some L0 of A, L0 of B, which will be some combination of the sin 0 of A, sin 0 of B, which are our degenerate states. Now we will take this as our unperturbed state, and we will do our non-degenerate perturbation theory that we did more or less similar for the default case as well. Now, because of this perturbation, LA will be equals to this plus lambda times L order 1 A, okay, and so on. Similarly, my B state will be equals to L of the 0th order of B plus lambda times L of the 0th order of B, and so on. Alright, and so instead of remembering the formula, I'm just going to solve it. So if you just have two states, so you can, instead of remembering, you can solve. And energy ELA, now what will be energy ELA? That will be equals to energy En, whatever our En value is. Okay, and let me just write, okay, this En value. I will write this as in this form, En of the 0th order and En of the 0th order. En of the 0th order plus lambda times E L comma A of the first order plus lambda square times E L comma A of the second order, and so on. Similarly, E L comma B, now this will also give me for the 0th order, it will be E n of 0 only, E L A comma 0 and E L A comma because let me just mention it here, because E L comma A 0 equals to E L comma B 0 equals to E n of 0, because these are degenerate states in the 0th order. You will write similarly E L comma B now of the first order, that is just simply writing L comma B in second order, and so on. Alright, so this I will call my set of equations as A, this set of equations as B. Now and what we know is h cap naught plus lambda times our h cap prime. Alright, we have our some perturbation. Let's say our perturbation is V. Let h cap prime is equals to V, which is our perturbation. Let's write it like this. H cap prime equals to V, which is our perturbation. So I am denoting this as some potential V. I am just denoting this thing as some potential V that I will apply. I have L comma L of A, that will be equals to some energy L comma A, L of A. Similarly, I will have h cap naught plus lambda times V. Let's say I will say lambda times V cap potential, not a constant but as some V cap potential, because generally in perturbation, like, we apply some kind of potential only, a time independent potential that we are applying. There will be some L comma B, L comma B. Let's say this is our equation number C. Now plug A, B into C and correct lambda to the power 1 terms. Okay, so that will be equals to h cap naught minus, so if you do this, if you do and correct the lambda to the power 1 terms, then you get epsilon 2 out of the power 0 L of the, sorry, minus potential V. Whatever V is our partition, without hat I am writing, head of the zeroth order comma A. Similarly, you will get h cap naught minus epsilon 2 of the zeroth order L of the first order comma B is equals to epsilon LB of the first order minus V times L to the power 0 comma B. Okay, so this is the similar way what we got in the non-degenerate case as well. Now now we will use our condition that we say that L0 comma A, I will say, is a linear combination of 0 2 comma A plus beta times there will be some alpha times our state, which is psi n of 0 comma A plus beta times psi n of 0 comma B. So so we know that we write this L0 of A as a linear combination of these two states. Now just say this is equation number D1 and this is D2. Now plug into D1. Okay, and what we will do is what we will do is what we have done earlier, and then we will multiply from left by psi n of 0 A and psi n of 0 B, psi n of 0 B. Okay, so we are going to multiply it by our degenerate cases both. So what you will get is, okay, so let us plug it into D1. So if you plug this thing into D1, if you have to plug this equation psi n of 0th order of A and this, and then you have to, okay, so let me just do it for D. Okay, we have to do it for D1, and for D2 also it will be the same thing. So our D1, if I write D1 condition, so first let us do it. H cap naught minus epsilon of 2 of 0 times L1 of A okay, that will be equals to epsilon LA of 1 minus V times L0 of A. Now I will write L0 of A as alpha times psi n 0 of A plus beta times psi n 0 B. Okay, and then first I will multiply with by psi n 0 of A from left. So what we will have is psi n of 0 of A times h cap naught minus E n of 0. Okay, 1 minute. I wrote here it will be E n of 0. Right. E n of 0. H cap naught minus E n of 0 L1 of A, that will be equals to epsilon LA1 minus V times psi n of 0 of A with alpha times psi n of 0 of A plus beta times psi n of 0 of b. Alright, so from here, now h cap naught will act on this psi n of 0 a, which will give us E n of 0 of a. So here you will get E n of 0 minus E n of 0. E n of 0 will come by this h cap naught will act on this and will give you this. Alright, h cap naught will act on psi n of 0, giving you E n of 0. So you will get E n of 0 minus E n of 0. So that term will be cancelled out, and what we are left with will be, so we can write this now as so this term will be 0. So this will be equals to 0. Equals to 0, because you can see this will be E n of 1 minus E inverse, so this will be equals to 0. And then we will have this term okay. Okay, let us write this whatever we have. Okay, sorry, I guess okay, we have done, okay, I did one mistake. Okay, yeah, it will be psi n 0a acting on E LA1 minus V times this. Alright, so applying this on here, what we are getting is psi n of 0 of a times EL. Now EL of a of 1, so I will have alpha times, alpha I can take common, EL a of 1 minus V minus V cap, so V cap times psi n of 0 of a plus beta times psi n of 0 of a ELA1 minus V cap times psi n of 0 of b. That has to be equals to 0. Now from here, what we have is, now EL of a of 1 could be taken common, and sin 0 of a of 1, this will give you 1. So what we will have is psi n of 0 of a V cap psi n of 0 of a minus epsilon LA of first order correction times alpha plus, now here now remember that here this term here, note that this since these are energy eigengets, so here also we have this thing, this psi n of 0 of a psi n of 0 of b will be equals to 0, because these are eigengets. Okay, these are energy eigengets of h cap naught. So although they are degenerate, they will be orthonormal. Okay, so this will be orthonormal, and since these are orthonormal, we get the remaining term will be just psi n of the 0th order of a okay, I've taken minus wrong. Okay, so I've taken a minus sign here, So so here we also we will get a minus sign, so that minus will get plus. Just check the minus sign here once. Sin of 0 to a, we get v cap, and this will come out, and sin 0 of a, sin 0 of b are equals to 0, so that will give you 0. I have to skip a little step. First time, so we will get this thing. Okay, so this will be our let's say this will be our equation, some E1 equation. Similarly, okay, now similarly by applying multiply by sin of 0 of b from left, okay, and if you do that, then what I'm writing this equation numbers. Let me just write this equation number with a bright color, so that I can see the equations. This is equation A. This is equation B. This is equation C. This is our equation number D. And this is going to be our equation number E1. And similarly, just by solving this, we get another equation that will be equals to psi n of 0th order, comma A, comma B, B, p cap, psi n of the 0th order, comma A, times alpha plus psi n of the 0th order, comma B, b cap, psi n of the 0th order, comma B, minus epsilon LA of the first order correction times beta equals to 0. So we have this E2 equation as well. Now we will just so we are again now arranging E1, E2 as matrix. So we have just derived the similar matrix. Instead of a D4 degeneracy, we did it for the 2-4 degeneracy, which is much easier to see. As you can see, like, we got the two equations in terms of alpha and beta. Okay, we have alpha and beta, and just using these two equations, let me just bring it here. Okay, so basically what we did is, till now we have considered 2-4 degeneracy, and we applied this h cap naught. We know this is our 0th order wave function and the energy eigenvalue, and we know that when we apply this v on, if you provide these perturbations, then what will happen? Our 0th order correction we also have to consider. We can consider that it happens actually like it is stored into some linear combination of these degenerate states. So we consider this states as our now the 0th order state, and then we applied our perturbation theory, and we got equation number A and equation number B for these two 0th order eigenstates, which is L0 sum A and L0 sum B, which we know are going to be some linear combination of these degenerate states. Then and the 0th order energies was this. Then we applied our we apply our same equation, and we got the terms from lambda. If you take lambda to the power 1 terms, then you will get these kind of D equations for A and B. They are similar. Then we will use the fact that this new zeroth order correction that we are seeing, they are going to be something like this. Okay, so here I am. So this will be a linear combination. Let's say alpha times some psi n of the zeroth order of A, and beta times some that other degenerate state. Then what we will do is we will plug this into our D1 equation that we got from lambda power 1 terms, and then what we did for a non-degenerate case, that we are going to multiply it by that first by the both the degenerate state, one time by sine of 0 of A and sine 0 of B. Doing this, we can get these two equations E1 and E2. All right. So we got this two equation E1 and E2. Now arranging E1 and E2 as a matrix, what we will get is psi n of the zeroth order of A, V cap psi n of the zeroth order of okay, let me just write it. Okay, so here we are. Okay, now arranging them in a matrix form, we have psi n of the zeroth order of A, V cap psi n of zeroth order comma A, and then I can write psi n of the zeroth order comma B, B cap psi n of the zeroth order comma A. I will have psi n of the zeroth order comma A, V cap psi n of the zeroth order comma B, and psi n of the zeroth order comma A, V cap psi n of the zeroth order comma B times alpha beta, that will be equal to epsilon LA of the first order times alpha beta. All right. So we got that alpha beta value, and similar equation could be obtained if instead of, okay, so you can check it here. So we just wrote these two equations in the matrix form. Okay, so it will be this minus alpha times of this, and this will be minus beta times of this. All right. So so we have just written this. Now we can express in so basically we have expressed our this V cap in our degenerate space, and that is what we did for in the lecture for the D4 space as well. Okay, so so this is the similar kind of equation that we obtain, and you can see that this is just an eigenvalue equation now within our 2-4 case, and so for two, if we just consider two 4 degeneracy, then we can simply see that there is an eigenvalue equation here, what we did, and thus this is going to be our eigenvalue. So this says that so ELA1 is eigenvalue, is eigenvalue, and we have expressed V cap is expressed in degenerate space. So we have right now, so we have proved it. So so this implies that our first order energy correction to psi n of the zeroth order A and psi n of the zeroth order B is eigenvalue obtained by diagonalizing our matrix this, which is V11, V12, V21 and V22. Okay, which is our this matrix. Okay, so this could be written as, okay, or this could be written as a V matrix, VAA, VAB, VBA and VBB. So VA, VAB, B and VBA. So you have to diagonalize this matrix, and what we will obtain after diagonalization will be what we have written. We have L0, we have considered it L0 of A. Alright, so we said that instead of this, they will become L0 of A, L0 of B. So they will, so you can write it as a diagonalization of this V cap, L0 of order A, 0, 0, L0 of B, V cap, L0 of B. So basically, we have just changed our ground state, and this will be, and these eigenvalues will be our first order energy correction. And this A and B doesn't matter. You could have taken at this step where we have taken this equation to be this at this step you can either take L0, you can either take D1 equation or the D2 equation, and you will get this similar equation. So the main point is this is what we have derived. So you have to just so we can see this problem as from this 2-4 degeneracy, and you can just compare it with the D4 degeneracy as well. You just have to make a V matrix, and then we have to diagonalize it. Okay, and resulting values we can find. Okay, so and this will be our energy eigenvalue will just be in this form. All right. So this I proved instead of like D4 degenerate case, we have proved it for the 2-4 degeneracy to understand it better what will happen, and we got a similar kind of result as in D4. All right, so we are already out of time. Okay, so in the end, let's just quickly see all the assignment number 4 problem as well, and then we end this tutorial, this session. Okay, so the first one was the first order perturbation E1 by this is applicable to the ground state alone. So that is not true. Like we know that this En of 1, we have when we have written psi n of 0, h cap prime psi n of 0 divided by normalization also you can see. So here n could be it is so n is we didn't say it is ground state or excited state, could be any. So correct answer would be B. It is false. It could be excited state as well. Second question was the second order correction E2 to the ground state energy is always negative. So it is written that it is for the ground state. So yes, like the second order correction formula, we know it. Summation of m naught equals to n. We have psi m of 0 h cap prime psi n of 0 whole square divided by E n of 0 minus E m 0, and like we solved some question, we solved that perturbation harmonic potential question as well, and there we got minus h cross omega. So generally we solve it for the ground state, and for the ground state you will get this negative value. But we can say that generally this m value is greater than n, or you can also say that even if you say some excited state, it is for the ground state, but even for the excited state as well, there could be many excited states. So most of the time we have many other states, so that could add the negative value as well. But generally we solve for the cases where n is not very high. It is close to ground state, so that's why the answer is A in this case. And always more number of, you can find more number of excited states than the state in general. You can find more number of excited state. Excited states, then the state n for which we are correcting energy. So generally in that case, then the value of we will get higher values of m, and it is generally for the ground state, so that's why the answer is B. Okay, now this third question was a one-dimensional particle in a box potential is perturbed such that the potential is raised by a constant V0 in the left half of the box and lowered by V0 in the right half of the box. What is the first order correction to the lowest energy state? Now we know that, okay, so here this is given as, and we know the first order energy correction, as we know, will be given by psi of the zeroth order to the lowest energy state as well. You can take, or you can take for as it is in the solution also, it is given for psi n for any energy state n. क्या? नहीं है. Sine of zeroth order, h cap prime sine of the zeroth order. So this will have. Now, so from here, what you will write is as this will be from integration from 0 to L, which is the length of your particle in a box. Okay, so sine of 0, you have a potential. Okay, you have your h cap prime sine of 0. It's a dx, and as given by the definition, up to 0 to L by 2, it will be sine of 0 of x times it will be V0 sine of 0 of x dx plus integration from L by 2 to L sine of 0 of x minus V0 sine of 0 of x dx, and that will be 0, and that is what given here. Alright, so next problem is E0 of 0 and E0 of 1 are zeroth order energy and first order energy correction of the ground state of a given system whose true ground state is W, which is the following relation is correct. So as given, it is because of the using this variational principle. So what we have taken is that we have taken psi naught is the ground state wave function of the unperturbed system, which is used as a trial function for the full Hamiltonian. So you can take it as the trial function, and then you can see that whatever this energy, this will be, and psi is the actual ground state of this h cap prime of our h cap. So this energy W will always be less than or equals to this energy, which will be formed by the trial wave function. So this is self-explanatory. The explanation is correct, so we don't have to do any calculation. Then an electron moves in a harmonic potential V equals to half kx square, and an external h cap epsilon x is applied. What is the first order energy correction to the first excited state? So here you have used a symmetry argument. So symmetry argument, you can use a symmetry argument, or you can see that to the uh, to the first excited state. Now remember that for the first excited state, psi 0 of x is given by under root of 2m omega by h cross m omega upon pi h cross to the power 1 by 4 x times e to the power minus m omega x square by 2h cross. All right. So this is your first excited state for these harmonic potential. Now here, your first order energy correction, if you do, then it will be psi 1 of the 0 of x. These are real functions, I am not including this. This will be your potential epsilon x. And again you will have this psi 1 of 0 of x dx. Now here, here you can see that by symmetry argument x, where these are order, whatever the integration. Okay, the integration that you will do will from minus infinity to infinity. So it is given a perturbation is an odd function, which is, we can see perturbation is epsilon is odd function, and unperturbed wave function, they have definite parity, so their parity is also -1. So what will happen is that when you do this integral, you will get some function, you will get some constant times x cube dx, and this is an odd function. So integration from minus infinity will be 0. So you can see it from this integration as well, that the answer should be 0. Okay. Next is the symmetry argument of the ground state of water is E1, and an electric field H prime is applied. Excited state of its symmetry species may be mixed with the ground state by this perturbation. So the answer is given, and it is self-explanatory. It is similar to in the lecture the symmetry argument that was given by it is given in the class. So it is regarding to that symmetry argument. So you can check it, and the solution is correct. Okay, so solution is easy, so it will be B1. All right, then okay, next 7th question. This was also basically based on just the symmetry argument only of this wave function and the perturbation. Then the seventh problem is the polarizability volume is given by this, and by what would be the change in the dipole moment in the of this molecule when it is subjected to an external electric field of strength this. Again, the formula is given, so this is just you have to put all these values. So just in case if you have some problem, so you just have to put all the values in SI unit, all the values in SI in given SI units, all right, and it is given that and your answer delta nu will be in, answer. Okay, so will be in Coulomb meter, which is for data moment. Okay, so divide the answer by 3.36 into 10 to the power minus 30 to convert it to divide. So this is just a formula based question, and if someone has any problem, then most likely it was how to do the unit conversion. You just have to put whatever the units are given or are given in SI unit. You will get your answer in Coulomb meter, and then you have to just divide by the unit conversion, which is given 1 divide equals to 3.336 into 10 to the power minus 30 to convert it to divide. Okay, and your answer will be A. Next is the oscillator strength of a transition at 160 nanometer 0.2. What is the mean positive volume of this molecule? Again, this is also again a formula based question. So you just have to put your values in it, and you will get the answer. You don't even have to do the unit conversion. Next is a hydrogen atom in ground state is perturbed by a uniform electric field along z direction. Which of the following statement is or are correct? Okay, so this we can discuss. So here for this correction, okay, for the first statement, A statement is that a first order energy correction. So what is going to be the first order energy correction? So if we do the first order energy correction on our ground state, which is our 1s state, if we do the first order energy correction, that will be given by psi 1s of the 0th order minus epsilon r cos theta times psi 1s of the 0th order. Okay. Now from the symmetry argument, what is written is that if you see this function, okay, now what psi 1 of s is psi 1 of s of the 0th order. It is approximate, it is given by, if you remember, it is e to the power minus r upon ab. So this is an even function. So again, by symmetry argument or by integration, you can see that this is going to be an even function. This is going to be an even function, while this is going to be an odd function when we do the integral. So if you apply the parity on an r of an r function, then that gives you r of r. So basically when you apply the parity operation, then r goes to r, theta goes to pi minus theta, and phi goes to pi plus phi. So when so by this you can understand like how the integrations are going to be. For this case, we can get this integral in some form. So what we will get is some minus epsilon times some integration from 0 to infinity r square e to the power minus r upon ab, and then you will have a potential r dr. So basically this r square comes from the integration d tau. Remember that when we have to do d tau integration, it is given by r square dr sine theta d theta. So when you have to do this integration, basically what if you write E1s of the first order correction, that will be basically psi 1s of 0, it will be a function of r. Then you have your minus epsilon r cos theta times psi 1s of 0th order of r times d tau. D tau is given by r square dr sine theta d theta d phi. Okay, so when we do this integration, we get from 0 to infinity r cube e to the power minus 2r upon ab dr. Here one r square will come from this d tau, and one r will come from our perturbation. Another integration will be from 0 to pi. We will have sine theta cos theta d theta times 0 to 2 pi d phi. So this integral will be equals to 0. Okay, this r cube to the power minus 2r ab, this will not be 0, it's from 0 to infinity, positive r values only. But this 0 to pi integral, if you check sin theta cos theta d theta, that will be 0, and that is coming from our odd function of this thing. So you can do the symmetry argument, or you can solve this integrals. So that's why this will come as 0. So this will become as 0. So our first order correction will be 0. So this is wrong. And similarly, second order energy correction to the ground state is 0. There is second order correction now similarly. So you just have to take you can either go with the symmetry argument, or you can do the mixing as we have done this for this one case, and you can check that that will be non-zero, which is going to be negative due to polarization, because it will be PZ mixing. And C will be contribution of the 2s orbital to the first order wave function is 0. 1s now in 1s 2s where the perturbation is 0 from again C, now the C we can say is correct, because we have proved that this kind of integration, we have proved that is 0, and we will have the this what we have this kind of equation, and it is asking the contribution of the 2s orbital, which will also have the similar symmetry as psi1s, to the first orbital wave function correction is 0. And again, if you remember the formula, then there will be this h cap prime times psi1s and psi2s. So again, in that case also we will get the 0 value because of similar kind of integration. Similar kind of terms will come because of this sin theta cos theta integral term will come. So that will make it 0. So that's why C is correct. And again, you can check that D is wrong. It will be non-zero. All right. Now, last question was starting from the Hamiltonian of a hydrogen atom. This use the Hellman-Feynman theorem and obtain 1 by R, which is the following is correct. Okay. Again, this is the what we have done. How to use Hellman-Feynman form. So delhi by. So what we will do is, since the Hamiltonian is given, we can see that. We have to find the average 1 by R. So first in this Hamiltonian, you can see that 1 by R is coming in just in this last term. So if I and in the last term there is E is also only in the last term. So if I use this Feynman theorem and I differentiate with respect to E, then I don't have to take care of the first two terms, and I just have to take care of the last term, and then you will just get this equation. And here let me just do this differentiation. So you can get this differentiation as minus 4 m e square upon 2n square h phi square by 4 pi epsilon naught whole square. That will be equal as minus 2e upon 4 pi epsilon naught average of 1 by r. That is just, I am just doing the differentiation here. Okay. And then you can just you can cancel out all these terms, and remember that this thing just cancel out this as well. We cancel out these two as well. So we will left with m e square upon n square h phi square upon 4 pi epsilon naught equals to, cancel this e as well. So we have m e. We have m, so there was meq. Okay, so we have m e square will be there. Let me just not cancel this thing. If we just get minus 4 m e to the power e cube, we have 2. We have minus 2e upon 4 pi epsilon naught. All right, and you can do the cancellations. You can do this minus will cancel out. These terms will cancel out. This will become 2. You can cancel out this here. So what we will get here will be just m e square upon n square h y square 4 pi epsilon naught equals to 1 by r. Okay, and a naught is given by 4 pi epsilon naught h phi square m e square. So this is equals to 1 upon a naught. So that's why our answer will be equals to average of 1 by r equals to 1 upon n square a naught. And that is what is written. So this is also just formula based. All you have to do is just understand like which term, which other parameter you have to differentiate with. And here we can see that it should have been with E, because then you don't have to take care of the other two terms and you are getting 1 by R, which is asked. Okay. So that is all for this week, and thank you for your time.